Alright, so the topic is momentum, and as the title suggests, momentum really, to find momentum of an object, you literally just multiply the mass of that object in kilograms times its velocity in meters per second. So mass times velocity, that's what momentum is. It's the product of an object's mass and its velocity. And if we were going to write it out in an equation format, we'd say P, because that's the algebraic symbol for momentum, is equal to mass times velocity. Usually I don't put the little x in there for multiply by. So velocity, mass, momentum. And just the fact that we have m already standing for mass is good enough reason to not use m again for momentum. So it's p. And momentum is a vector. Now, if velocity is a vector and mass is a scalar, oopsie, it does make sense that momentum would be a vector, because if you take, let's say, a force and you multiply it by 5, you just get a bigger force, and it would still be in the same direction that the original force was in. A scalar times a vector will still produce a vector. A scalar times a scalar always produces a scalar. It does get a little bit tricky when you have a vector times a vector, because people that have started with the calculus course know that sometimes you have dot products and cross products. So it depends on how you multiply a vector times a vector. But a scalar times a vector is always a vector. I want to talk about the units, though. The units for mass, kilograms. The units for velocity, meters per second. And so the units that we get when we calculate momentum are kilogram meters per second. There isn't a fancy abbreviation like when we talk about force. You know, force was kilogram meters per second squared, and that was a Newton. And there isn't a fancy abbreviation like joules, where you have the composite units being simplified as joules. We just write it as kilogram meters per second. There's no simplification. Okay, so this kind of looks like the ugly cousin of the joule and the Newton, but oh well. Hey, what are you going to do, right? I want to talk about something that might have some momentum. So for example, this is obviously either a bowling ball or a coconut. It's a bowling ball. I want to put it on some level ground. If the bowling ball has a mass of 5.00 kilograms, and if we say that the bowling ball goes that way, and we say that it has a velocity equal to 2.00 meters per second, let's make to the right positive. And we'll make to the left negative. And I said, hey, let's calculate what the momentum of this bowling ball is. Well, we can say, okay, momentum is equal to mass times velocity, or 5.00 kilograms times positive 2.00 meters per second, because to the right is positive, and you end up getting 10.0 kilogram meters per second. And we would say it's positive, which indicates that it's to the right. Cool. Very straightforward. So we're starting off with baby steps. What about this? Let's say that I have, I can never quite draw these properly. This is a swallow. You know the bird, the swallow? Let's see, and I can't tell from the drawing whether it's an African swallow or a British swallow, but it is a swallow, okay? And the swallow can fly. We'll say that it's going to fly to the right with some velocity. But it has a mass equal to 0.0500 grams. 50 grams. I'm sorry, not grams. Kilograms. Kilograms. So about 50 grams. Little tiny swallow. Okay. What I'd like to know is, could you figure out what the velocity of the swallow would have to be so that it would have the same momentum as a bowling ball? Sure, why not? We just say, all right, so whatever the swallow's velocity is, it's got to satisfy the momentum of the bowling ball, which we said was 10.0 kilogram meters per second. I'd like to figure out what the velocity of the swallow would have to be to have the same momentum as a bowling ball. I mean, that would be a heck of a thing. So I could say P equals mv, or V equals P over m, or 10.0 kilogram meters per second divided by 0.0500 kilograms. I need some help with the calculations here, but I can see that the units, kilograms on the top, will cancel out with kilograms on the bottom, and it'll leave me with units of meters per second by the time this whole thing is done. So 10 divided by 0.05, 200, yeah. So about 200 meters per second. Or if we wanted to show significant figures, we could say 2.00 times 10 to the power of 2 meters per second. 200 meters per second, though, that's a fast swallow. That's like, it's faster than what most people would sort of consider to be the projectile velocity for a handheld weapon. So this is a very fast swallow. Realistically, is it reasonable that you might find a swallow with the same momentum as a bowling ball? Oh, probably not. Although, if you had a swallow hitting a window with the same momentum that a bowling ball would if you threw a bowling ball out a window, do you suppose that the swallow would go through the window? Probably, yeah. Assuming that the elastic properties of swallows don't make it just splat when it hits the window. Yeah?
Is the P for momentum supposed to be a capital or what?
It's an uppercase P for momentum. Momentum, like pneumonia. Yeah. No, uppercase P. Alright. So you would have to go pretty fast as a swallow to have the same momentum as a bowling ball with a fairly low velocity. Let's take a look at maybe a more realistic scenario. Let's say that we have a transport truck. I can never quite draw these things properly. I don't spend enough time around transport trucks.
So it's pretty good. Yeah, that's impressive.
Don't your kids watch machines?
Pardon me?
Don't your kids watch
Great show.
machines?
No, we don't watch Mighty Machines in our house. Not yet. Not yet.
That was a great show.
So let's say that we know that the mass of this transport truck is 30,000 kilograms. Nice round number. 30,000 kilograms. And let's say I want to take it at a very slow speed. I want to give it a velocity of 0.00500 meters per second. I mean, check that in terms of what it means. It means 5 millimeters per second. Okay, that's real slow, right? Real slow. And if I want to give that a directional reference frame, I'm going to, again, make to the right positive. I'll just draw it on top of the smoke there. And to the left, negative. And very simply, I can calculate what the momentum would be for this transport truck. So I'm doing this not because it's a difficult calculation, just because I want to talk about momentums. And you'll find if you take 30,000 kilograms and multiply it by 0.005 meters per second, 150?
Yep.
Okay. 150 kilogram meters per second. Or you could say 1.50 times 10 to the power of 2, but I'm going to leave it at 150. Now in the same, let's say on the sidewalk, on the same street even, you could have a roller skater. And you can tell this person's a roller skater because they have roller skates on. That's a good way to tell, right? All right, so there's a roller skater. And I'd like to say this roller skater has a mass of, 80.0 kilograms. Okay? And they're happy because they're roller skating. 80 kilograms. I'd like to figure out what a reasonable speed would have to be for this reasonable mass roller skater to have the same momentum as that transport truck. So I could say that, again, P is equal to mv, V is equal to P over m, and we're going to check to see how fast a roller skater would have to go to have the same momentum as a great big transport truck that's barely moving at all. Okay? So momentum, 150 kilogram meters per second, mass of 80 kilograms. What do you end up getting? Yeah?
1.875.
Sounds about right. 1.875 meters per second. Now, that's actually a reasonable speed. 2 meters per second for a roller skater, you could do a little under 2 meters per second if you're a roller skater. The thing is, you're going at a pretty decent speed, a little less than 2 meters per second, but that's just to have the same momentum as a transport truck that's going at 5 millimeters per second. 5 millimeters per second, oh my goodness. That's like only slightly faster than a slug. Like, that's very slow, and that's just to match momentums. Mass really matters when it comes to momentum. You can compensate by going faster, but mass really matters. I want to take a look at a brick for a second. Why not? Because bricks definitely can have momentum. Okay, so one of these like cinder block type bricks. And I'll write out the equation, but I just want to have it there so that we can talk about it freely. Momentum equals mass times velocity. Now, if this velocity were 0, what happens to the momentum of that brick? Yeah. Okay, so I'm just going to say it as an if-then. If the velocity is 0, then the momentum is 0. What about if I talk about it in terms of the mass? If the mass is big, tell me about the momentum. Still 0, right? If the velocity is 0? Yeah. Doesn't matter. If a big mass is sitting still, and it's sitting still, and it's sitting still, the momentum's 0. Now, the reason I bring this up is because some people get this crazy notion that momentum and inertia are the same thing, because they think to themselves, I remember that things in motion tend to stay in motion, and if it's got a lot of mass, it has a lot of inertia. And so they say, well, momentum is something in motion, and it has a lot of mass when you're dealing with, if it has a lot of mass when you're dealing with momentum, then inertia and momentum must somehow be the same thing. If the mass somehow contributes to momentum and the mass also contributes to inertia, they're not the same thing. One's a calculated value, and it has its own meaning, and the other is a tendency. Things with a lot of mass tend to stay in their state of motion. Now, if they're sitting still, they're going to tend to stay still. They're going to have a lot of inertia because they have a lot of mass. If you have a lot of mass but 0 velocity, you still have 0 momentum. Inertia and momentum are not the same thing. And somehow, people in regular, everyday conversations in the English language seem to get them confused sometimes. They talk about, oh man, look at that kid go. He's an awesome hockey skater. You can still see that he's going to go all the way to the top in the NHL. He's got a lot of momentum. Another person might say the same thing and say, yeah, there's nothing that can stop that kid. His inertia is going to carry him all the way to the top of the NHL. And they might think that they're saying the same thing. But saying that people have a lot of momentum and saying that people have a lot of inertia, boy, oh boy, you could live a very sedentary lifestyle and have a lot of inertia. You just tend to stay put. Okay? Very, very different. Hockey's not a bad illustration for it. What about kinetic energy? You notice that EK, kinetic energy, is equal to 1/2 mv squared. I mean, what's the point of having momentum if we already had an equation that took care of those two variables? Why would you ever care? What's the difference between kinetic energy? Do you think? This is a cursory look. But in terms of the properties of kinetic energy and momentum, what's a major difference between the two? Yes? V squared, so there's maybe an embedded dot product. Tell me about vectors.
When you're multiplying vectors.
When you multiply vectors,
Yeah.
you get scalar.
Yeah, this guy's a scalar. That's a scalar property. This guy's a vector. That's a vector property. One's a vector and one's a scalar. Now, you can actually conserve momentum without conserving kinetic energy. And we're going to talk about how that can happen later on. But these two, they're not the same thing. They happen to have the same variables, but they are not the same thing. No more are these two the same thing than inertia and momentum are the same thing. They are not the same thing. They happen to share some properties. That's about all we will say. But they are not the same thing. I just want to make sure that people know that before we even go any further.